So we're looking at second order non-homogeneous differential equations, still linear equations, right? And still only with constant coefficients. But the theory doesn't require the constant coefficients here, but the only ones we'll solve will have constant coefficients. The thing is, we're trying to solve something that looks like this up here. And so we need to find a y that when we multiply it by b and multiply the derivative by a and multiply the next derivative by, well, by 1, that those will combine together to look like g. And it's like, well, if g was already a function that was kind of nice and that maybe its derivative looked kind of like itself, then the second derivative would also kind of look like itself, and you'd be able to combine them together and get something that looks like g, then that would be nice. So I want to find functions whose derivatives look like themselves. First candidate, of course, would be polynomials. Derivative of a polynomial is another polynomial, 1 degree less. Right? Exponential functions. Derivative of an exponential is also an exponential. Right? Maybe times a constant, but still, it looks very much like it started with. You could combine the a to the x with that, and factor out the a to the x. Right? It'd just be some other constant times a to the x. So exponential functions definitely are functions whose derivatives look like themselves. Sines and cosines are kind of almost there because it takes 2 derivatives to get back. So the thing is, if we combine them together, right? If I take a linear combination of sine and cosine, then the derivative will be a linear combination of sine and cosine. Now, if the sine and the cosine have different periods, so the b here is different than the d there, then it doesn't immediately look, I mean, it's still a sine and a cosine, but it's a different, this was a cosine with b, this is now sine with bx, and this was a sine with d, and this is a cosine with d. But if b and d are equal to each other, then this is really nice because the derivative of that linear combination of sine and cosine is a different linear combination of the same sine and cosine. The derivative of this cosine bx becomes a sine of bx, and derivative of the sine of bx becomes a cosine of bx, but still, now you have a linear combination of sine bx and cosine bx, which is what you had before, right? So this definitely has a derivative that looks like itself. Those perhaps you could have come up with. I think less obvious, I know for me, I needed to point it out that, hey, when you take a product of these things, the derivative of that product is still looking like what it started from. That is, if I have a product of this polynomial and this exponential, that I use a product rule, then I can factor out the exponential, and what do I have? Well, I have a product of a polynomial and the same exponential. Right? In fact, it's the same degree polynomial. This was a squared times e to the 2t, and I still have a second degree polynomial times e to the 2t. So yeah, the derivative of a product of polynomial and exponential is a polynomial times an exponential. Likewise, I could do an exponential times a linear combination of sine and cosine. Use the product rule, gather some like terms, and I've got the exponential times a different linear combination of sine and cosine. And I see I have a typo here, that this cosine right here should be sine. Well, I'll have to fix that. So, when we're doing this method of undetermined coefficients, we will really only be doing it when the g looks like a product of polynomials, exponentials, sines, and cosines. Now, it may not be a product, it may be a sum of them. Sums are easier to work with than products, but at least it has polynomials, or it has exponentials, or it has sines and cosines, and any combination of multiplying or adding them together. We'll do some examples in the next video.